In section 3.5, we're going to look at the linear equations in terms of applications of problem solving. Linear equations can be used to solve many real-world applications. In this section, we offer guidelines to write equations to solve applications and consider the following problem-solving flowchart. The first step when trying to solve any kind of applied math problem is to first of all read the problem completely. Oftentimes, this can require you needing to read through the problem more than once in order to kind of gather all of the important information. Especially on the first passing through, you want to familiarize yourself with the problem and specifically be able to answer the question, what am I trying to solve for? Like, what is this problem asking me to find? Okay. Um, and then if you can kind of have some kind of intuition going into the problem as to what you might expect, that can oftentimes guide us to a reasonableness check at the end of it to see whether does our answer makes intuitive sense or perhaps not. The next thing we're going to do is assign labels to the unknown quantities, and typically these will be our variables. Typically, whatever you're trying to solve for, let's suppose you want to solve for a student's grade on a test, then for example, let x be the test grade. If you wanted to solve for how many hours the person has to work during the course of a week, again, you could let x be the hours worked. It's also common practice, especially if you're doing applied problems. Like if you're trying to solve for, let's say, like a student's grade, maybe instead of using kind of the generic variable x, you'd use maybe the variable g, just kind of reminds you that it stands for grade. Again, if you wanted to figure out how often or how many hours a person works during the course of a week, you could use like the variable h for hours or maybe t for time. But you have to assign labels to what you're trying to solve for. Okay. The next thing that is we want to write down an equation in words. And this is kind of a pseudo step between the worded problem and the mathematical equation that's going to govern that situation. Okay. So if you can verbalize what is the important things that are at play here, and especially trying to start to relate, okay, how does the information that I'm trying to find relate to the information that's given in the problem? If you can answer that question, that a lot of times will help you to set up your diagram or to diagram out the sentence in an equation. And then we're actually going to write the mathematical equation out. So we're going to try to write an expression like we've been doing in the previous sections, something that we can use our algebra skills to solve for. And then once we solve the equation, we want to interpret the answer. If it's a real-world problem, then you should be giving a real-world answer. That means writing in complete sentences and describing exactly what was being asked for. Okay. In order to kind of help us out along the way, there are some common English phrases for the four basic operations. For the operation of addition, sometimes you'll hear the phrase sum, something plus something, something added to, the phrase more than, increased by, or even total. Those are all words that indicate the operation of addition. For subtraction, we typically say a lot, we'll say the difference. The difference of A and B means A minus B. Or you could even say B subtracted from A decreased by B, or you can say A less than B. These are all words that indicate subtraction. For multiplication, sometimes we'll just say multiply, sometimes we'll say times, or the word product all means multiplication. And for division, some of the synonyms are quotient, A divided by B, B divided into A. We could even say the ratio of A and B, A over B, or A per B is another common one. Another phrase that I like that's not on here is split evenly. So if you're taking something and dividing it up or splitting it evenly, this also indicates division. For example, let's suppose you have 4 friends that go out to lunch and the total bill is $20. If those 4 friends split the bill evenly, then obviously each person would pay $5 for the lunch, which is found by doing 20 divided by 4. Okay. Let's take a look at example 1. In example 1, they say a number decreased by 7 is 12. Find the number. Okay, so pretty straightforward. We're looking for an unknown number. That's the gist of the problem. I don't know what the number is, so and I'm just going to let x be the number. They already kind of describe the situation in words. A number decreased by 7 is 12. So we should be able to take this sentence and directly translate it into our mathematical equation. The number, we don't know what it is, so we're calling that x. Decreased by means subtract 7 is it's going to be your equal sign. That's how that translates. And equals 12. A number decreased by 7 is 12, means that x minus 7 equals to 12. This is our equation. We now want to go ahead and solve this. To get the x by itself, we're going to add 7 to both sides. And we get x equals 12 plus 7 is 19. Again, that makes sense. We know that if we take 19 and decrease it by 7, 7 less than 19 does give us 12, so that is the correct answer. And let's verbalize and write out our answer. We would say the number is 19. Again, a worded problem should be responded to with a worded solution. The number is 19. Let's take a look at another one. 7 less than 3 times a number results in 11. Find the number. So this is another situation where we're looking for some unknown number. I don't know what the number is, so I'm going to introduce the variable. Once again, I'm going to say let x be the number. They give a verbal description of something that the number satisfies. 7 less than 3 times the number results in 11. Let's be very careful in trying to translate this. When we read it off, it says 7 less. So some people might immediately start saying 7 less like this, but that would not be correct. When you say something is 7 less than it, that means you need to take 7 away from it. So 7 less means to subtract 7 from something. What are we subtracting that from? 3 times the number. For us, that's going to be 3 times x, which we know we represent as 3x. And then when they say results in, that's just a fancy way to say equals. So equals 11. So our worded problem translates to the equation 3x minus 7 equals to 11. This is the thing that we have to solve. Each side is already simplified. The x is over here on the left-hand side. To isolate it, we would need to add 7 to both sides. This would give us 3x equals 11 plus 7 is 18. And then lastly, to get the x by itself, we would need to divide both sides by 3. So x equals 3's cancel. 18 divided by 3 would be 6. If we want to, we can check this out, run that answer back through the problem to see if it makes sense. 3 times 6 we know is 18. If I have 7 less than that, 7 less than 18 does result in 11. So this answer makes sense, and let's finalize it. We would say the number is 6. Let's take a look at another one. In example 3, it says 2 times the sum of a number and 8 equals to 38. Find the number. So it's similar type setup. We're looking for some unknown number. So to begin, I'm going to let x be the number. And now we want to see if we can take and translate this statement into an equation. Notice how it says 2 times. Well, we know that 2 times means 2 multiplying to something. Let's be careful here. What is the 2 multiplying to? It's not multiplying just to a number, it's multiplying to the sum. How do we write the sum of a number and 8? Well, that's going to be x plus 8. And it's very important. We have to have this parenthesis here. If you didn't have the parenthesis, if you wrote it like this, which is a common mistake that LC students will make, this would be the sum of twice the number in 8. But what we have twice of is the sum. So we have to do x plus 8 and then multiply it by 2. So we have to have this parentheses. And then obviously this part equals 38 is just simply this. So we translate it. This is the equation that we get. In order to solve this equation, step 1 says to simplify both sides first. That left-hand side can be simplified by distributing the 2 in. 2 times x is 2x. 2 times 8 is 16. Equals to 38. The next step, now that we have both sides simplified, we try to identify where is the variable at. It's only on the left-hand side, so our attention goes to there. To isolate the x, we would need to get rid of the plus 16. So we subtract 16 from both sides. We get 2x equals 38 minus 16 is going to be 22. And then for the last step, we would divide both sides by 2, and we get x equals to 11. Again, does that seem reasonable? Let's run it back through the problem. If we do 2 times the sum of a number and 8, well, 11 plus 8 we know is 19. And if we do twice 19, what does that give us? Well, 2 times 19 is 38, and so that's exactly what the problem says it should work out to be. So this is definitely correct. Let's state our final conclusion. We would say that the number is 11. Let's take a look at the next one. In example 4, they first ask us to write an expression. It says that Kathleen works twice as many hours in 1 week as what Kevin does. If Kevin works for h hours, write an expression that represents the number of hours that Kathleen works. Okay, so I'm going to let K, just because I know it's that for that person, I'm going to let K be Kathleen's hours. And so we want to write an expression here. Notice that her number of hours is related to the number of hours that Kevin works. And he works h hours, and she works twice as many hours as he does. So the expression should be K equals twice Kevin's, which is going to be twice h, should be 2h. So the expression for hers is just 2h. At a carnival, rides cost $3. If Alicia takes n rides during the day, write an expression for the total cost. So let's do that. So what do we know about the cost? So the cost is going to be the price per ride. So how much does each ride cost? And then times the number of rides. So the cost should be equal to the price per ride, which we know is 3. The number of rides is unknown, but they say let n be the number of rides. So it's going to be 3 times n or 3n. Let's take a look at the next one. It says Josie made $430 less 1 week than her friend Annie made. If Annie made $D, write an expression for the amount that Josie made. So here we have 2 people. There's Annie and Josie. It says Annie made $D, which we don't know, it's just a variable expression. But we know that Josie made 430 less than Annie. So Josie made 430 less than D. 430 less than D would be to take D and subtract 430. So D minus 430 would be an expression for how much Josie made. Let's take a look at example 5. In example 5, it says a carpenter must cut a 10-foot board into 2 pieces to build a brace for a picnic table. If one piece needs to be 4 times as long than the other piece, how long should each piece be? This is a classic type of application of a linear equation where not only are we trying to solve for one variable, in essence there's 2 things we need to find, because we need to find out how long is going to be each of these 2 pieces of board. If you want to, this is also a problem that you can kind of diagram that's very geometric in nature. So we have this 10-foot board. And notice we're not cutting it evenly. We're cutting it so that one piece is going to be 4 times longer than the other piece. So if you think of it kind of like here's piece 1. And then here's the bigger one, which I'm going to call piece 2. The technique here is we want to come up with an expression for each of these 2 pieces. I don't know the length of piece 1, but let me just go ahead and call that x. So I'm going to call the smaller piece, I'm going to call it of length x. We could, but it's a bad idea here. I could say, okay, if I don't know piece 2, let me choose a different variable because it has a different length, so it can maybe call that y. But we do know the length of piece 2 in relation to the length of piece 1, right? It needs to be what? 4 times longer than the other piece. So if I call piece 1 x, then the bigger piece I can represent by 4 times that, 4 times x, which is 4x. And by doing so, we now have a variable expression for each of our 2 unknown quantities. With a variable expression, the next step is we need to make an equation out of this. And what equation can we make? Well, we know how the 2 lengths relate to each other. If we add the 2 pieces together, that's going to make up our 10-foot board. So the length of the first piece plus the length of the second piece has to be equal to 10. This gives us our equation. We can now solve it. We have like terms on the left-hand side. X plus 4x is 5x equals to 10. Divide both sides by 5, and we get x equals to 2. That tells us that piece 1 is going to be 2 feet, and piece 2, which is 4 times x, is going to be 4 times 2, which is 8 feet. We can check this. Obviously, 2 plus 8 does give us 10. And the 8-foot board would be exactly 4 times as long as the 2-foot board. So that gives us the answer. We can write it out. So we could say one board or one piece is 2 feet and the other is 8 feet. Or any other way you would like to express it that conveys the length of both boards. Because again, at the end of the day, if you just say something like x equals to 2, you're really not answering the question. Because first of all, what is x? What does x stand for? And second of all, the problem was asking us for the length of each piece. So there's 2 numbers we have to report here, and that's the 2 feet as well as the 8 feet. Let's take a look at example 6. In example 6, it says one model of a 42-inch TV sells for $800 more than a smaller 32-inch TV. The combined cost for the 2 TVs is $2,000. Find the cost of each television. Okay, so pretty straightforward. We have 2 TVs, and we want to know how much each one costs. So once we kind of understand what's going on, we want to come up with a variable expression for each of these. And the easiest way to do this is we obviously want to start off by we don't know the cost of either one. So we want to let X be the price of one of the two TVs. It's always best in a word problem like this, whenever they compare the price of one to the other, to let the variable be the one that everything is being compared to. When I reread the problem, it says one model of a 42-inch TV sells for $800 more than the smaller 32. What that means is that everything is being compared to the price of the 32-inch TV. So that's the one you want to let equal your X. That comparison will then give you an expression for the other variable. For the 42-inch TV, it's $800 more than the smaller one. If the smaller one is X, then the larger one, the 42-inch, must be 800 more than X, which would be X plus 800. We've now successfully come up with an expression for the price of each of the two TVs. So the next step is we need to go to an equation. The equation is going to be brought about because the combined cost of the two is $2,000. So if we take the price of the 32-inch TV, and if I add to that the price of the 42-inch, in total this should add up to $2,000. We now have our equation. Let's solve this. X plus X gives us 2X plus 800 equals 2,000. We want to isolate X, so I'm going to subtract 800 from both sides. We get 2X equals 1,200. And then lastly, divide both sides by 2. Divide by 2, divide by 2. We find that the value of X is 600. That value of X represented the cost of the 32-inch TV. So that's going to be $600. The 42-inch TV is going to be X, which is 600, plus 800, which would be $1,400. We can check this very easily. Obviously, if we add the price of the two TVs together, the 600 plus 1,400 does give us a $2,000 total price. And notice how the 42-inch, which is $1,400, is exactly $800 more than the $600 32-inch TV. So we have our answer. Let's just kind of state it in words. So the price of the 32-inch TV is $600, and the price for the 42-inch TV is $1,400.